Hi students, in this video we're going to talk about continuity. So our main idea for continuity is that a function is continuous at a point if the limit as you approach the function value is equal to the actual function value. Implicit, we would have the limit has to exist, the function is defined, and again, the limit as we approach the function at a particular value is actually equal to the function value. So when a function is not continuous, we're going to have the criteria that either the limit does not exist at the point, the function is not defined at the point, or both the limit exists and the function is defined, but they're not the same value. So when we discuss the continuity for a function, we state it in terms of intervals, in terms of the independent variable. So generally, we work with x and y. So when we're expressing our continuity, we're going to say x, and it has a certain interval where the function is continuous. So for this first example, we have this graph of a function, and we want to state where the function is continuous. All right, so we can actually get some infinities involved here. We're going to extend this graph out to negative infinity, and we'll say this graph goes up to positive infinity. Doesn't really matter. That part doesn't really matter. So when we're looking at the graph, we can see that from negative infinity to 2, the function is continuous. So we say something like f of x is continuous. I will spell the whole thing out. So f of x is continuous on the interval. So one interval that the function is continuous on is negative infinity to 2. We don't include 2 because the function is not continuous at x equals 2. We'll talk about that in a moment. Then the function is also continuous on the interval. We'll say that's like 2 to let's go with 2.75. So 2 to 2.75. We'll put a bracket because we can actually equal that. And then the function is also continuous on the interval. We'll call it 3.25 up to 4, and then union 4 to infinity. So that's where the function is actually continuous. So let's talk about where it's discontinuous and state the kinds of discontinuities. So, all right, one discontinuity is at 2. So we'll write discontinuous. So discontinuous. All right, so this function is discontinuous at x equals 2, and that's going to be because the limit as x approaches 2 for f of x does not exist. So if we go back to our definition of limits, when we approach 2 from the left, we end up at positive 2, but when we approach 2 from the right, we end up at 4. So our left limit and right limit are not equal. So that first criteria for continuity is violated. And so our function is not continuous here. Generally, when the limit doesn't exist at a point, this is going to be called a jump discontinuity. Jump discontinuity. The next kind of discontinuity we have happens at x equals 3. I think we all know what that one is. X equals 3 is a vertical asymptote. And then let me erase this. So then at, what's our next one? We have x equals 4. And so at x equals 4, we have a hole in the graph. So we have a hole, and a hole is going to be what we consider a removable discontinuity. And generally, when we have a removable discontinuity, we're going to have a hole where the limit is headed. So the limit is going to exist at that point, but the function is not actually defined at that point. It is not necessary for a removable discontinuity that the function is actually defined. The limit just actually has to exist there. So this point that we have at 4, 2 is not entirely necessary. It does help give the function a value. So in this case, this will be that third case where we have the limit exists at the point and the function is defined at the point, but the limit and the function value are not the same thing. So that is why the function is not continuous at x equals 4. So let's write that. We'll write this all in red. So hold on. So what we said is the limit as x approaches 4 for f of x is not equal to f of 4. The limit as we approach 4 is actually 4, but f of 4 is 2. So obviously 4 is not equal to 2, so the function is not continuous. So for our second example, we want to determine if the function is continuous at x equals 1. So again, our criteria are 1, that the limit exists. So the easiest way to evaluate the limit is to substitute in the value. So let's see. The limit as x approaches 1 from the left for f of x. So if x is less than 1, x is not equal to 1. So that means that we can use the top part of the piecewise function. And so then if we substitute in 1 to that, we're going to have 1 squared minus 6 times 1 plus 5 divided by 1 squared minus 1, which seems like we're going to get 0 over 0. So remember, like, if we end up with the indeterminate form, one thing that we can do before we try to find a limit is actually factor it. So let's factor this expression first, and we'll factor it up top. So hold on, excuse me, take that out. So let's see. So x squared minus 6x plus 5 is going to be x minus 5 times x minus 1, and then divided by x plus 1 and x minus 1. So obviously our x minus 1s cancel. So we can rewrite this function to be x, what do we say, x minus 5? So x minus 5 divided by x plus 1 if x isn't equal to 1. So here, now we can easily write our limit as x approaches 1 from the left for f of x. That's going to equal, so now if we so again, if x is approaching 1 from the left, that means x is less than 1, which means that x is not exactly equal to 1. So when we substitute in 1, we're going to get 1 minus 5 divided by 1 plus 1, which is negative 4, divided by 2, which equals negative 2. And then the limit as we approach 1 from the right is going to be the same thing, because if we're approaching 1 from the right, like 1.01, that's still not exactly equal to 1. So we can still use the upper function. So we're going to get 1 minus 5 divided by 1 plus 1, which is still negative 4 divided by 2, which equals negative 2. So what we know is that the limit, because the left limit and the right limit are the same, the limit as we approach 1 is equal to negative 2. So that first criteria, that the limit exists, is met. The second criteria, that f of 1 exists, is also met. So I think f of 1 was 3/2. And so now our third criteria is, does f of 1 equal the limit as x approaches 1? And so for that, we're going to get no. The limit as x approaches 1 for f of x, which is actually equal to -2, is not equal to f of 1, which equals 3/2. So if determine if the function is continuous, we would say no, the limit as x approaches 1 for f of x is not equal to f of 1. And so this is how we would justify this not being continuous. So polynomial functions are continuous everywhere, which means that their interval of continuity is -infinity to +infinity. Rational functions are going to be continuous everywhere except where we have vertical asymptotes, which is a non-removable discontinuity, or where they have holes, which are removable discontinuities. So for example 3, we want to determine where the function is continuous. So first, let's factor this. So we're going to factor the numerator to be x, I believe x minus 5 times, we'll say x plus 2. And our denominator factors to be x plus 8 and x minus 3. So it seems like we have two vertical asymptotes. So our interval of continuity, we would say f of x is continuous on the intervals. So obviously, because they're both polynomials, so we could have -infinity to -8 union -8 to 3 union 3 to infinity. And x equals -8 is a vertical asymptote. And x equals 3 is also a vertical asymptote, because neither one can be factored. So that makes it a vertical asymptote. So let's do a slight addendum to this problem. For whatever reason, imagine that this term instead was x minus 3. So just so we're clear, what we're doing for example 3 is done. We found where the function is continuous, and we stated the kinds of discontinuities that we have. So now I'm just doing something extra, where imagine that we had x minus 3 here instead. So for this addendum, then we would say x equals 3 is a removable discontinuity, which means it's a hole in the graph. And then x equals -8 would still be a vertical asymptote. So our function would still be continuous on this interval these intervals that we've defined, but then x equals 3 changes to be a removable discontinuity because the factor x minus 3 can be divided away. All right. So an important consequence of continuity is the intermediate value theorem. And what the intermediate value theorem says is, if a function is continuous on a closed interval, then if there's a value between the two outputs of the endpoints of the interval, there has to be an x value that produces that output. So if we had to draw an example of the intermediate value theorem, it would look something like this. So let's draw an xy axis. So then let's zoom in a bit. So let's say we had a point here, we'll call this A, and then we'll call this point here f of A. So this point is a f of A, and then we'll have another point over here B, and up here, we'll call this f of b. So this point is b f of b, and this other point is, we'll write it over here, but it's a comma f of a. Cool. So there are a couple of ways that if the function is continuous, it means that when we draw our graph, we basically don't pick up our pencil. So the easiest way to get from point A to point B is to go in a line. So what the intermediate value theorem is telling us is that you don't skip values between these output values. So assume here, we'll draw a dashed green line. So assume, all right, that's too high. Let's undo that. So let's assume right around here is the line. So we'll call this line y equals k. It's some number between f of a and f of b. It's greater than f of a, is less than f of b. So for this output k, then somewhere between a and b, there's a number c that produces this output. So we'll color this yellow. So like right at this point here where we get k, there is an output value, there's an input value of c that produces this. So at this point, that would be c f of c, and f of c just equals k for simplicity's sake. So somewhere between these 2 points, there is another point that guarantees this input value. So like say I told you that, we'll take an easy function. So if I give you f of x equals x squared on the interval 0 to 3, then we know f of 0 is equal to 0, and we know f of 3 is equal to 9. What the intermediate value theorem is going to tell us is that since the output values are between 0 and 9, there is for sure a value that gets you 4. So here, we'll say the intermediate value theorem says there is some x such that f of x is equal to 4. Now we know what the value is between 0 and 3, that if I square it, I get 4. Namely, that's going to be x equals 2. That's what the intermediate value theorem will tell you, that there's a value that has to give a certain output, and that value has to be between 0 and 3. So 4 is between 0 and 9, and the value that produces 4, which is 2, is between 0 and 3. So for our fourth example, so the intermediate value theorem is it can be used to justify that a function has x-intercepts or zeros on a particular interval. So what we have to do is show that the function f of x equals x cubed minus x squared minus 2 has a solution on the interval -1 to 2. So first, what we need to show is f of -1. So f of -1 is -1 cubed minus -1 squared minus 2, which is -1 minus 1 minus 2, which equals -4. So then f of 2 is going to equal 2 cubed minus 2 squared minus 2, which is 8 minus 4 minus 2, which actually equals 2. So because f of -1 is 4, because f of -1 is -4 and f of 2 is 2, so the intermediate value theorem applies because f of x is continuous on the closed interval, is continuous on the interval -1 to 2, and f of -1 equals -4, and f of 2 is equal to 2. So between the values -4 and 2, to get from -4 to 2, you have to equal 0 at some point. So because 0 is between, we'll just abbreviate that, between -4 and 2, f of x must have a 0 between -1 and 2. Now, what that 0 is, that's not up to us. We'll learn other methods for finding zeros for functions that can't factor. That's something that we'll do when we get to Newton's method. So all we have to do is say the intermediate value theorem applies here. And so for the last thing is, for class on Wednesday, just look up and define left continuity and right continuity. So that's going to conclude our video on continuity. The big thing here is that for a function to be continuous, it has to meet these three criteria. The limit has to exist, the function has to be defined at the point, and the limit has to equal the function value. A nice consequence of this is the intermediate value theorem. And that's it. So I'll see you all in class. Thanks for watching.